Tiene el micrófono abierto, ¿eh? ¿Y pueden ver si pueden compartir pantalla? ¿Si pueden compartir pantalla?
Sí, para que se duplique la pantalla. Ah, ya. Es que no se veían.
Mira, ahí ya se ven ellos.
Ahí está bien la licuadora.
Creo que sí, ¿no? Sí, no tendría que ir acá, pero yo creo que ahí está bien.
No, los que están en Zoom van a ver lo que se puede.
Ajá, en su pantalla. ¿Sí puede compartir pantalla o tengo que...? Es que no sé si tengo habilitada esa opción. ¿Puede checarla? Sí. No sé. No es lo que quiero saber si les aparece la opción.
Pero para presentar,
Sí.
pues debe estar.
Ok.
Así que lo vemos.
Apagamos eso. Gracias, sí. Ahorita me voy a decir que la estoy usando. ¿El sonido? ¿Es en la torre?
Hola a todos.
Bienvenidos, espero que me escuchen también tanto los que nos miran en YouTube. Bienvenidos a un seminario más del Departamento de Matemáticas Aplicadas y Sistemas. Hoy nos vestimos de manteles blancos, tenemos un gran invitado. Le doy la palabra al doctor Chacón para que sea él quien nos introduzca al profesor que nos acompaña.
Buenas tardes. Por el invitado vamos a hablar en inglés. Entonces, si tienen alguna duda de la presentación, si no pueden hablar en inglés, yo tampoco, entonces me dicen que yo los puedo traducir para darle preguntas al profesor. So let me introduce Trifce Sandev, Professor Trifce Sandev from the Macedonian Academy of Science and Arts. He's also an associate professor of theoretical physics at the Faculty of Natural Science and Mathematics in Skopje, Macedonia. Macedonia is, for now, is a country for the former Yugoslavia. And Professor Sandev, after completing his PhD in 2012, he was postdoctoral researcher at Max Planck Institute of Physics for Complex Systems in Dresden, Germany. His areas of interest are stochastic processes, anomalous diffusion, fractional calculus, and many others. He appears as an author of more than 90 scientific papers. By Springer and Core Scientific. He was awarded by the President of Macedonia for the youngest scientist in the country in 2011, and recently, very recently, by the Chef Award in, just last year, in 2023, for particular achievements in the field of science for the Republic of Macedonia. He has also awarded by the Alexander Grunberg Fellowship for experienced researchers for doing research in the Institute of Physics and Astronomy in Potsdam, Germany, during 2020 to 2030. And also he's a member of the Society of Physicists in Macedonia and the European Physical Society and the German Physical Society. So Professor Sandev will talk about, let me share the screen. He will talk about anomalous dynamics, but first let me share the screen. ¿Está? ¿Cómo control? That's it. No, we don't have. Okay, just. I'm not sure if this pointer. Okay, I don't know. Okay, sorry. Yeah. So please.
Thank you, Guillermo, for the kind introduction. My name is Trifce Sandev. I'm from the Macedonian Academy of Sciences and Arts, Skopje, Macedonia. And I'm glad to be here. This is my first time in Mexico. I visit Puebla for a conference, and now Mexico City is a very nice country, so definitely I will come again. And the weather is very nice because now in Macedonia it's -5, so it's very cold. So I'm happy to spend some time here during our winter. So I will talk about anomalous dynamics, complex systems. That is my topic of research for more than 10 years. And I will present some general overview in the field. So I will give some introduction and I will present some new calculus that is needed to describe such processes of anomalous diffusion, and then I will present some models that can be used to model such processes. So anomalous diffusion is something that goes beyond the normal Brownian motion. We all know what is Brownian motion. It appears when we have a massive particle immersed in some liquid, for example, in water, and because of the interaction of the molecules of the water with the particle, then if we measure this, the mean square displacement, we will see that it has a linear dependence in time. So if the mean square displacement is proportional to time, then we have that this process is classical Brownian motion or normal diffusive process. And this normal diffusion can be described in different ways. One of them is the Langevin equation, which is a stochastic differential equation. It's like a second Newton law, where the force that acts on the particle is a random force. So this is the difference. And here we have the friction in the system. And if we solve this equation by Laplace transform, we can easily calculate the mean square displacement. And again, we will show that the mean square displacement has a linear dependence in time, like for this Brownian motion. And the velocity correlation function has exponential decay. So these are signatures of normal diffusive process. So if you have questions, you can interrupt me during the talk. Don't wait till the end of the presentation. So another approach to describe classical Brownian motion or normal diffusion is with this partial differential equation for the probability density function. And this probability density function means what is the probability to find the particle at position x at time t. And if we solve this partial differential equation, we will see that the solution is this distribution, which is called Gaussian distribution. And if we calculate the mean square displacement, we just integrate x squared multiplied by the distribution, we will see that the mean square displacement has a linear dependence on time. So this is another approach to normal diffusion or Brownian motion. And this equation was derived independently by Einstein and Minkowski in 1905 and 1906. So these are two different ways to explain the normal diffusive process.
Excuse me, the D is stochastic.
The D is diffusion coefficient. Yes, D is the diffusion coefficient. So I already said that the normal diffusion has a Gaussian probability density function, and the mean square displacement is linear in time. But if this mean square displacement is not linear in time, but has a power law dependence, where alpha is different than 1, then we say that this process is anomalous diffusive. If alpha is less than 1, between 0 and 1, then we say that this is subdiffusion. If alpha is greater than 1, then we say that this is superdiffusion. And for alpha equal 1, we have normal diffusion. But also there are other processes more complicated where the mean square displacement has, for example, logarithmic dependence on time, which means that the process is very slow. And there are also other processes where the mean square displacement has a logarithmic on time, but to some power. And if this power is equal to 4, this is a very well-known Seminario diffusion. So there are many physical and biological systems or in chemical systems which shows this anomalous diffusive behavior, like anomalous transport in biological cells, in artificially crowded systems, in active transport in living cells. So in all these systems, there are many papers nowadays, experimental works that show different systems shows anomalous diffusive behavior. But in many systems, there is a characteristic crossover, which means at the beginning, the particle behaves like subdiffusion, and after some time, it behaves like normal diffusion, or vice versa. And then we need some simple model to explain such characteristic crossover. In the past, this was done that people explain that in the short time we have subdiffusion, we use this model, and in the long time limit, it shows normal diffusion. We use another model. But our aim is to find one simple model which will describe the behavior of the particle in the short, in the intermediate, in the long time limit. So this is one example of subdiffusive system. This is a conformational dynamics of this fluorine oxidoreductase, which contains fluorine, adenine, dinucleotide, and tyrosine. And if we have photostimulated emission of electron from one of these parts to which is donor and acceptor, then this starts to vibrate. And if we measure the mean square displacement of these vibrations, we will see that the mean square displacement has a power law dependence of time, which means that we have a subdiffusive behavior in the conformational dynamics of proteins. And if we measure the velocity autocorrelation function, we will see that we have power law decay of the velocity autocorrelation function, which is different than the exponential decay. This is another system which shows superdiffusion, and this is a active transport in living cells. If we follow the trajectories of these black dots here, particles which are pigments, melanophore, then if we follow the trajectory of one of these particles and we measure the mean square displacement, we will see that it has p to power alpha, where alpha is greater than 1, which means we have superdiffusion.
Where is that? I mean, what is that medium? Where
this is in the living cell.
Inside.
Inside, yes. So this is a system, and usually when we have active transport, the resulting process is in the living cell. The resulting process is superdiffusion because we have active force that drives the system. And such anomalous diffusion usually appears in crowded systems. So if we follow the movement of one of these fluorescent dark proteins in such crowded environment in biological cell, we will see that it moves subdiffusively. And this system looks like the movement of some particular person in the Sao Paulo underground station, because the environment is so crowded that he cannot freely move, and because of that, it starts to move subdiffusively. So these are some systems, but there are many others that shows this anomalous diffusive behavior. And the people that work in this topic of anomalous diffusion, they say that anomalous is normal, which means that there are more systems that show anomalous behavior than normal diffusive behavior, and there are very faint and review papers and other articles that explains that in many different systems you can observe this anomalous diffusion. So anomalous is not. It's not anomalous. As I already said, that there are different models for description of this anomalous diffusion. It's continuous time random walk, fractional diffusion, Fokker-Planck equations, distributed order, fractional Brownian motion, fractional Large equation, and many others. So if we solve such models, the resulting process is anomalous diffusive. But for example, if you calculate the mean square displacement from the continuous time random walk theory with long waiting time, and we calculate the mean square displacement for the generalized Langevin equation versus fiction memory kernel, I will show you later, is a power law, the mean square displacement will be the same. But these two processes are totally different. The first one is non-Gaussian process. The generalized Langevin equation is a Gaussian process. So when you try to describe some experimental data or data from simulations, it is not enough just to calculate the mean square displacement and to say, okay, I will use continuous time random walk because the mean square displacement agrees with the experimental results. You need to calculate other, for example, velocity autocorrelation function. You need to find probability density function in order to be sure that this model is a good model for your data.
Is that just a mathematical coincidence, or there is some relations between these different
There-
approaches?
No, between these two, no, but it's just this is a partial differential equation, and it looks if we go from standard diffusion equation that I showed you before, and the standard Langevin equation, and we generalize the standard Langevin equation to the generalized Langevin equation, introducing memory kernel, and we generalize the diffusion equation by introducing memory kernel. So you do in the same way. And then if we just calculate the mean square displacement, they are the same, exactly the same. But both processes are totally different. This one is Gaussian, this one is non-Gaussian. So, but if you know that the process is non-Gaussian, then you can say, okay, maybe it's continuous time work model. But if the process is Gaussian, then you should see maybe it's a fractional Langevin equation. I will show you later that these two are very similar models, but are different. In one we have internal force, in one we have external force. So this is the only difference in the model. So I said that in order to describe this anomalous diffusion, we need another calculus, not standard calculus of integration and differentiation introduced by Leibniz, but we need this so-called fractional calculus. And fractional calculus appear nearly in the same time with the standard calculus, and there is a conversation between Leibniz and L'Hopital that Leibniz asked L'Hopital, can the meaning of derivatives with integer order be generalized to derivatives with non-integer order? And then L'Hopital answered, what if the order n will be 1/2? So it's not first derivative, it's not second derivative, it's not third derivative, but it's derivative of order 1/2. What will happen? And then Leibniz answered that it will lead to a paradox from which one day useful consequences will be drawn. And at the beginning, really there was a paradox because not in a consistent way was introduced this fractional derivatives. But nowadays, at least in the last 20 years, it is used by many authors to describe this anomalous diffusion. And the first problem is the Tautog problem of Abel, in which fractional derivatives and integrals appear, but Abel was not aware of the fractional calculus, and they just solved that if we have a movement of a particle through this line in a gravitational field, and we want to calculate the time needed the particle from some position to reach the origin. And if we solve this equation, we will see that in the final solution, there appears some memory kernel, which is a power law memory kernel. But we will see later that this is exactly the fractional integral and fractional derivatives. But they just solved the problem without using these fractional derivatives, but now we can apply these fractional derivatives to solve such a problem. And there are different fractional derivatives integrals, but mostly used is, for example, Riemann-Liouville fractional integral. It is a generalization of multiple integration. So if you have a multiple integration of a given function, this is 1/n-1 factorial, and this integrals here. So you can show this by mathematical induction that is correct. First integral, second integral, comma integral, comma plus 1 integral, you will show that this formula is correct. And what is fractional Riemann-Liouville? Just what will happen if n is non-integer. And if n is non-integer, then this factorial becomes gamma function. And then we have 1/gamma mu. And here we have, instead of n, we have u. So this is a Riemann-Liouville fractional integral, is a generalization of multiple integration, where the order of integration n can be non-integer. And there are some properties of this integral, but I will not go in details. And the Laplace transform of this fractional integral is s to minus u. Laplace transform of the function, which is a generalization of derivatives of integrals. Laplace transform of integral is s to minus 1. Laplace transform of the function. Second integral s to minus 2. So this is just generalization. And from the Riemann-Liouville fractional integral, we can introduce removable fractional derivative, which means that this is a fractional integral, and then we differentiate the fractional integral. And in the Caputo, first we do differentiation of the function, and then we have a fractional integration. So both fractional integration and differentiation are in opposite order done. And these two are mainly used by many authors to describe this anomalous diffusion, especially Caputo, because the Laplace transform of Caputo derivative in the Laplace transform appeared the initial values at 0, as in the normal derivatives. And we need some other special functions, not exponential function or Gaussian distribution like for the normal diffusion, but we need Mittag-Leffler function. Used for Mittag-Leffler, he was a Swedish mathematician and founder of still one of the best journal in mathematics, Acta Mathematica. And he introduced, at the beginning of 20th century, he introduced so-called one-parameter Mittag-Leffler function, where this is a sum, and instead factorial here, if we have factorial, this is a simple exponential function. But if instead of factorial we have a gamma function, this is a Mittag-Leffler function. If alpha is equal to 1, we see that Mittag-Leffler function goes to the exponential function. If it is 2, it goes to cosine function. If this is minus, for example, and if this is plus, this is cosine hyperbolic, and if it is 1/2, this is error function. So this is a generalization of exponential of trigonometric functions, and this appears as a solution of this fractional equation. So if we have an eigenvalue problem, instead of first derivative, we have fractional derivative. The eigenfunction of this eigenvalue problem is the Mittag-Leffler function, and it looks like this, depending on alpha. And which is important, it has a power law asymptotics for large argument, and it has a stretched exponential behavior for small arguments. And these properties are very useful in the anomalous diffusion because in the long time limit we have some power law relaxation, and these Mittag-Leffler functions show such behavior. There are generalization to 2 parameters, where if this one is not 1 but it's some beta, then this is called 2-parameter Mittag-Leffler function. So if both alpha and beta are 1, it is exponential, but then these are some useful properties. It can be also sine hyperbolic function or different combination of exponential and other functions. So they are not general than the 1 parameter, and this is how it looks the plot of these functions, and also it has a power law decay for large arguments. And there are generalization to 3 parameters. It is
Una conferencia. Necesito que me encuadres el puesto.
equal to 1. This is the. Is there some, maybe some has a question or I don't know.
Ponemos el cuadro.
Sí, todos me caso.
Sí. Any question?
Ya pues.
In Zoom?
No entiendo la referencia. ¿El te quieres burlar? ¿Cómo se llama? Sí, espero que usted.
También hace cosas de cocina.
No sé qué.
No, I thought that someone wanted to ask something. So there are different asymptotic behavior.
I want to say that because usually in mathematical methods or special functions, we study, for instance, the hypergeometric function. That we also see that for special values of the parameters, we obtain the easy functions like the trigonometric, the power law. Is there a relation between Mittag-Leffler generalizations and hypergeometry?
Yes. I will show you later that Mittag-Leffler is a special case related to a slight Fox function, and Fox function is related to hypergeometric function, but for some specific values of the parameter. And then you can generalize this to n parameters. So you just put more and more parameters, but it can be easily calculated. So I don't want to talk about this, but just to know that there are many other more complicated functions, and we can plot them with mathematics, for example. And the one parameter and two parameter Mittag-Leffler functions can be plotted in mathematics. There is a with Mittag-Leffler, I don't know, Mittag-Leffler A, in, and then you just put the argument and the order of this parameter alpha. So you can simply plot in mathematics Mittag-Leffler function. So now I will speak about one of the models of anomalous diffusion. This is called generalized diffusion equation, which is a generalization of the simple diffusion equation. And usually this can be derived from some random walk model. This is a simple two-dimensional random walk model, but this can be simplified to one dimension. What does it mean? That we have a particle moving with equal probability left and right. And each step is with equal length. So if we write the master equation for this random walk in one dimension, what does it mean? That at time t plus delta t, the particle at the position x can come either from left or from right with equal probability, 1/2, from left or from right. And if we expand this by Taylor expansion, then we will see that at the end, we do the Taylor expansion, we will derive this diffusion. So from simple random walk model, we derive the diffusion equation, which is a explanation of the normal diffusive behavior. But for example, if the probability the particle to comes from left or from right is not 1/2, is not equal, which means we have different probability from left and from right, we do again Taylor expansion. So like this, it's very simple. And then at the end, we will find that corresponding equation describing such a random walk model is the diffusion equation here, but we have some additional term with potential or external force. And this external force appears because of the different probabilities to go to left or to right, which means that there is some force that acts on the particle, that the particle moves preferably in one particular direction, which can be explained by this potential function or external force. So these are two simple random walk models from which we can derive the simple diffusion and Fokker quantum equation, and then we can calculate the mean square displacement, and we can find that the mean value of x in case of constant external force is related to the mean square displacement if there is no external force. This is known like a second Einstein relation or linear response. There is a relation between this and this in case of external force and without external force. But there are more general processes when the particle doesn't move with equal probability left and right, and the length of the jumps of the particle are different, which means once the particle makes this jump, another make this jump, and then bigger jump and moving in the other direction, which means the particle makes different jumps, and between two jumps, it stays at the position, which means it is trapped. It doesn't move because of some of the geometry or some potential or whatever. And we can derive simple, it's not simple, but in a similar way like for the Brownian motion, we can write the master equation, and then we can solve this equation, and we can find the probability density function in Fourier Laplace space, which will depend on the waiting time, what is the distribution of waiting times, and of the jump length distribution. What is the distribution of jumps of the particle? And for different distributions, we have different equations. So if we have exponential waiting time and we have a Gaussian distribution of jumps, we can arrive to the simple diffusion equation. But if we have a long waiting times, which means the particle stays longer and longer while moving, then a resulting process will be diffusion equation, but here instead of first derivative, we will have this fractional derivative. So the fractional derivative appeared in the system, as a result of the waiting time. The power of the waiting time appears as a power of the fractional derivative. So as a solution, we have these Fox functions. I will not go in details, but this is a generalization of Gaussian distribution. So in case of normal diffusion, we have Gaussian distribution. In case of fractional diffusion, we have this Fox distribution. And if we calculate the mean square displacement, we will see that it has a power law dependence on time. So anomalous diffusion appears in the system because of the long waiting times. Because the particle is trapped in, while moving, it can be trapped. It doesn't stay for the same time all the time while moving left and right. So this is a simple example of anomalous diffusion. But also if we have, for example, exponential distribution of waiting times, the particles wait like for the normal Brownian motion, but the distribution of jumps is not Gaussian, but is a Levy distribution. Then we go in the equation and we will see that we have a space fractional diffusion equation instead of second order derivative in respect to X. This is called Trifce fractional derivative. But also can be combination of both, which means the particle stays longer and longer while moving, and the distribution of jumps is not Gaussian, but it's a Levy distribution. So we have combination of both. And if we do simulations for the same time, for example, this is for a simple Brownian motion, and this is for a Levy flight with waiting times. We run simulations for the same time. We will see that for Brownian motion, the motion is localized because the particle moves left or right with equal probability, and it doesn't make long jumps. But if we make long jumps for the same time, the particle explores wider environment. And birds use Levy flights when they search for food. They make a flight and then they search the environment. If it doesn't find food, then they make another flight, they search again, another flight. So this is like this, for example, of Levy flight.
Sorry, that what can I say? That path, that trajectory is just the long jumps, not waiting times.
No, these are
Just
long
Levy.
yeah, Levy flights. And also, there are papers in which the movement of people by planes can be considered like Levy flights with waiting time. Because when I came here, I start from Skopje, I make a Levy flight to Vienna, and then I stayed for 2 hours, like a waiting time. And from Vienna, I make a jump to Frankfurt, and I stayed 3 hours there. And from Frankfurt, I made a long jump to Mexico City, and I stayed there. And then Guillermo picked me up. We went by car to Puebla, and I finished my search. So this is another example of Levy flight with waiting times. And there is one nice paper in which they trace the transfer of money in US, say banks, which means that you have transaction of money from one bank to another, and then this money stays in this bank for some time, and then make transaction to maybe to another bank or to the same bank. And if we follow the distribution of money transfer, we will see that this space-time fractional diffusion equation can fit this experimental data. So, as I said, that anomalous diffusion appears in the diffusion processes where there is memory, and this memory appears in the diffusion equation by this gamma function. And we can solve this equation, and we can see that the mean square displacement depends on this memory kernel gamma. And for example, if this gamma is a power law function, as we showed before, this will be T to power alpha. The anomalous diffusion appears because of the power law memory kernel. And another process that can describe anomalous diffusion is a heterogeneous diffusion process, which means that we have diffusion coefficient which is not constant. In the Brownian motion, it means that the environment is homogeneous, which means that the diffusion coefficient in each part of the environment is the same. But there are many heterogeneous materials and environments in which the diffusion coefficient from one point to another is different. So it depends on the X. And because of this noise here is not additive, but is multiplicative. And then we can solve this equation. We can find the corresponding Fokker-Planck equation. We can calculate the mean square displacement, and we will show that it has a power law dependence on time. But also there are, for example, if alpha is here, the diffusion coefficient depends like x to power alpha. If alpha is equal to 2, then this is a special case of geometric Brownian motion, which is this process here, which is very famous in finance. This is the well-known Black-Scholes model in the finance, where the solution of this Fokker-Planck equation gives a log normal distribution. So this is a very well-known model in finance. The mean square displacement has exponential dependence on time, which means that the process is very fast. Exponentially grows the mean square displacement. So these are processes, and then we have heterogeneous telegraphers equations, which means that we have some additional terms in the equation, the second derivative. But this equation can be related to the heterogeneous diffusion equation by simple transformation. And if we solve this equation for a telegrapher's equation later, if you have some problems, the questions you can ask me for more details. We can solve this equation. It's this function, and then we can calculate the mean square displacement. Then we will see in the mean square displacement we have a 3-parameter function. And if we do analysis for short times and for long times, then we will see that the system from hyperdiffusion may go to hyperdiffusion, or from hyperdiffusion to ballistic motion, to superdiffusion, to subdiffusion. So depending on the exponent alpha, we have different crossover dynamics. Okay. And then I will show you generalized Langevin equation. The generalized Langevin equation is a generalization of this Langevin equation, where instead of the first derivative in the friction, so this is the solution of the Langevin equation. We can calculate the velocity autocorrelation function, exponential decay. We can calculate the mean square displacement. It has linear dependence on time. I already told you. But this happens when the particle which is immersed in the environment has a much bigger mass than the mass of the surrounding molecules of the surrounding particles. Because this particle is massive, then the interaction with the molecules is sudden, which means it happens just suddenly. But if the molecules of the surroundings are with comparable mass with the particle immersed in the environment, then the interaction cannot be sudden like in the simple Brownian motion. But they can stay together for a longer time. And because of this collision, instead of first derivative here, instead of delta function, we will have some memory function. So it appears in the friction. And this equation can be solved, and we can calculate the mean square displacement. So if we compare the mean square displacement for the overdamp regime, which means that the acceleration is small to the friction, we will see that the mean square displacement, we don't have this term here, has the same form like in the continuous time random walk model. So two different models gives the same results for the mean square displacement. But this process is Gaussian because the noise here is Gaussian, and in the continuous time random walk model, the process is non-Gaussian. And then we can calculate also, we can find that this linear response folds also in the generalized Langevin equation, but the process is different from the continuous time random walk model. And this is another approach. This is fractional Brownian motion. And it's a very similar, I will not go in details, it's very similar to the generalized Langevin equation, but here the noise is external, which means that there is no relation between the noise and the friction. In the generalized Langevin equation, the correlation of the noise is related to the frictional memory kernel, but here no, the noise is external. The processes are, and again, this model gives a power law dependence on time of the mean square displacement. We have totally different processes. And then application can be diffusion in cone. For example, the particle moves in some main channel, but while moving in this x direction, it can be trapped in the fingers of the comb. And because of this trapping, if we make simulations, we will see that the mean square displacement has a power law dependence on time with exponent 1/2, which is a signature of anomalous diffusion. And if we try to find the corresponding equation that explains the motion in this X channel, we will see that it is a time fractional diffusion equation where the first derivative is replaced by a fractional derivative for the 1/2. So there are many experimental works that can be explained by this comp model. This is a diffusion in a spiny dendrites. If we compare the form of the dendrite, we will see that it looks like a comb. And also, with these models, we can explain the transient diffusion of telomeres in the nucleus of mammalian cells. So if we follow the movement of these particles here, which are telomeres, we calculate the mean square displacement of this, it is observed that there is a transition from subdiffusion to normal diffusion. And there is an explanation why this transition appears, but because the particle performs like a continuous time random walk, we can use the generalized Langevin equation with power law memory kernel in order to explain the anomalous diffusive behavior of the particle at the beginning. But because after some time the particles goes to normal diffusion, then we should have cutoff of this memory. And this cutoff can be introduced by some exponential function. And if we put this memory kernel in the generalized diffusion equation, we calculate the mean square displacement, the results coincides with the experimental results. We have in this model transition from subdiffusion to normal diffusion. Also, these models can be used to describe, I already showed you this example. So for conformational dynamics of proteins, we can use fractional Langevin equation to model such system. And the corresponding results are very well from the theory and from the experiment. And then we can use tempered generalized Langevin equation, where this memory kernel has not just a memory, but has exponential cutoff. If we solve this equation, we will observe again transition from subdiffusion to normal diffusion. Yet it has been shown that such a model can be used to describe the lipid molecule dynamics in lipid bilayers membranes. So if you have some questions later, we can discuss, but I'm going to give some more details. So these are the lipid molecule dynamics. And if we compare the results from the experiment with the theoretical results, we see that with one simple model, we can get the dynamics in short times, in long times, but also in the intermediate times, simply by introducing a memory kernel in the generalized Langevin equation. So with this, I would like to conclude that there are fractional derivatives and Mittag-Leffler functions can be used to describe experimental results related to anomalous diffusion and relaxation processes, and that the fractional derivatives naturally appears in continuous time random walk models, and also, for example, in the generalized Langevin equation, when we have comparable mass of the inverse particle and the mass of the particles of the surrounding molecules. Because there are many papers, mathematical papers, in which the authors generalize every known law from standard to fractional. They say there is a fractional Maxwell equation, there is a fractional Schrödinger equation, fractional, I don't know, all the equations, but they don't justify the use of the fractional derivatives. You cannot just simply exchange the first order time derivative from the second order time derivative with fractional derivative. So you should start from some process, like in the continuous time random walk. It's a simple random process where we have waiting times is a power law distribution. And because of this power law distribution of waiting time, we derived the equation for the probability function. We found that instead of first derivative, we have fractional derivative, or in the common, because of the trapping of the particles in these channels, the corresponding equation is a fraction. But we cannot just say, I will generalize every equation to fractional, and I will discover new physics. No, you should start from a physical process and go back to derive the equation. And if appears fractional derivatives, okay. If not, okay again. But you cannot just simply use this fractional derivative. So at the end, I would like to thank Professor Guillermo Chacon Acosta, who invited me to come to Mexico. And I did my best to come because I needed visa to come here. And I was not, I was traveling a lot and I couldn't apply for visa, but in 1 week I get the visa and I come here. So now I have visa for 10 years. So I can come in the next 10 years more frequently. And also the institute here for the opportunity to give a talk, and these agencies that support my research in the last 3-4 years. And at the end, so I invite you with your colleagues and students to submit a paper in the journal Chaos. It's the American Institute of Physics journal. It's a very good journal. And there is a special issue in the Anomalous diffusion. The deadline is 15th of October, so everyone is welcome to participate in this special issue. And I would like to invite you to come to Macedonia. So in September, we have a conference in Ohrid. It's a conference of the physicists of Macedonia. It is every second year, which means it was in 2022. Guillermo was there. For the first time last year, he came again, but not for the conference. I hope Guillermo and some of you will come in September. So this is the Ohrid city, Ohrid Lake. It's a nice lake. And the city and the lake is protected by the UNESCO. But also you can spend some time in Skopje, where there is a this nice, also like artificial lake, and you can enjoy our mountains. So thank you very much.
Thank you, Trifce, for your nice talk. So if you have some questions, maybe we can have some time. Again, you cannot speak in English, you can ask in Spanish and then. Okay.
You said before that in a part two stays sometime in some place. It depends, or it will affect it be affected by geometry.
Yeah, it can be affected by geometry.
You're talking about curvature and some kind of.
Yeah, it can be also. I know that Guillermo works on these different geometries, and we are discussing to apply such models in such geometries. As I showed you, for example. So if we have this simple two-dimensional, let's say, cone, and we are interested in the movement of the particle in X direction. And while moving here, it can be trapped here, and it cannot jump from here. So this is prohibited. The particle should come again here, and because the particle performs a Brownian motion in the fingers, the returning probability we know from the theory that is proportional to T2 minus 3/2. Returning probability of a Brownian particle at the origin. And this returning probability will play the role of a waiting time, because while the particle is here, it doesn't move in X direction. And this waiting time, if we put in the general form of the equation, we will see that the corresponding equation will be with time fractional derivative of order 1/2. But what will happen if we put fingers of the fingers? So we have here, which means that the particle, in 3 dimensions, the particle is trapped here, but then it can move in Z direction. Then it doesn't move in X, in Y direction, while the particle is stuck here. And because of this waiting time here, and this waiting time in this finger, then instead of 1/2, in the diffusion equation, we will have 1/4. The process is slower. The mean square displacement in such a case will be proportional to 1/4. Because the process is slower, because of this additional geometric constraint. But if you have some different geometrical constraints, then we should try to see what happens. Yeah, then it will affect the motion in the main channel. For example, in the underground water, if you put some tracer, and there are many cracks in the soil, then this tracer, when moving in this main channel, can be trapped in the small channels. And because of this trapping, it will go slower and slower in the main channel. So for different geometries, it should be tried to by simulations or with some approximations to find what will be the corresponding motion.
Thank you.
But we will be discussing with DMAS. Maybe we should try. We can discuss with you. No.
Further questions? ¿Más preguntas? ¿Alguna otra pregunta? Ah, sí, en Zoom hay alguna pregunta. Creo que pueden abrir su micrófono. ¿Sí? Oh, okay.
I have a question.
Yes, please.
You mentioned various biological applications like molecules using regulated by nature or stuff like that. So is this just like a mere descriptive model, or knowing how the diffusion carries out as a more practical application?
I'm not experimentalist, but as far as I know, if you have some active motion in cells, that the resulting process is super diffuse. But when you have the process, you should know a lot about the process. Is the particles moves all together, and then to apply maybe generalized Gaussian equation, or the particle perform like jump, like motion, and to apply the continuous time random model. So you should make a lot of analysis in order to be sure which model can be applied for such a system. But there is no general rule that for such a process. I don't know.
For instance, this can be a simple model. This right? A simple model for a neuron.
Like this finite dendrites.
And also the crowded medium inside the cell. Also, but it's just a first approach, first mathematical.
And then you can train different models with this machine learning and this Bayesian inversion and all this. There are many papers, and there is a competition each year. There is a competition. They give you experimental results, and then you test your model. And you have some time, and then different groups they are competing, and at the end they publish these results in Nature Communications. So all the participants in this competition are co-authors of this paper that is published in Nature Communications. So maybe you can make a group. I don't know. I think it's still open this call for this year, but if not this year, maybe next year. And yeah, we should make the training of the models and which models are the best. It is anti-challenge. Just anomalous diffusion challenge. Anti-challenge.
Another question? I would like if you can say a bit more about. Sorry,
Beyond the motion, there is thermodynamics, different thermodynamics. I wonder because, well, I asked because you're a diffusion equation. The diffusion equation is thermodynamic by analogy. So you consider thermodynamics, or you are just considered one particle, therefore thermodynamics.
You can consider also such a case, but usually that we are interested in these models in how to find the probability density function of an ensemble of particles that are moving diffusively, different constraints or without constraints, or with different potentials, totally the mean square displacement, velocity of the correlation function. So usually this is the interest of that we are doing, but also in this generalized function equation, then you, if this fluctuation dissipation theorem is satisfied, then you have like internal noise in the system, and if you don't have this fluctuation dissipation relation, you don't have this thermal equilibrium in the system. So some external noise. But there are some groups that are working for that, but I'm not very much involved in such investigation.
No questions, maybe? No, I just want to ask a couple of questions. You mentioned when you were talking about flights, you mentioned this exchange with banks and so on. What is exchanging? Just money, and I mean, what is the whole process that we can picture?
You consider the location of the bank here and there. Like you make immediate transaction of the money, because the levy flight means that you flight from one point to another immediately. It's not a real physical
Class.
flight, because you flight with infinite velocity, but you cannot fly with velocity. But when you make a transaction, the money are transacted almost immediately from one location to another location. So they consider distribution of banks in the US and how much money they are transferred, and how long the money stays in particular banks before it will be transferred to another bank.
But isn't it a network, like a complex network?
Yeah. Network of banks. But
each bank is in a node.
It is a node of the network, and with some approximation, you arrive to this space-time fractional diffusion equation that can explain such a distribution of time in the other banks. But there are more realistic models than levy flights, which means these are called levy walks. That the particle moves, but with some constant velocity. It doesn't make a jump immediately, but it needs some time from one particle to go to another particle. So these are levy walk models.
And they are even slower.
No, that can be also super diffusive or super diffusive, depending on the waiting time, on the velocity of movement of the jumps. There are different generalizations.
So, for the questions, I hope you can capture some of the highlights that Professor because look that these mathematical tools can be applied to some biological things, also economics and finance.
Yeah, because many experimentalists, they haven't heard about Mittag-Leffler function. And they fit some of the results with power laws or power law function or sum of exponential function. But if they know about the Mittag-Leffler, then they will see that they can fit with one Mittag-Leffler function very well this experimental data. Or also these fractional derivatives, some you haven't heard, but they exist and they can be useful. So,
okay, if there are not further questions, or in Zoom maybe. No. Ok, bueno, pues le agradecemos al doctor Trifce Sandev de la Academia de Ciencias y Artes de Macedonia haber estado con nosotros aquí hasta México. Entonces, pues, por favor.
So, thank you. Now we can enjoy some food property. Vas a decir algo.
Now we can jump into